now that we have defined affine subschemes of affine scheme, we can also have a nice construction of unions and intersections. And the good thing is that because the affine scheme records the full data of this ideal cutting it out, we get a very natural formula here. So assume you have two affine subschemes, spec R modulo J1 inside spec R and spec R modulo J2 in there. Then, well, we know, let's skip to this part here, then we know the underlying sets are V of J1 and V of J2. And then, well, what should the intersection and the union be? Well, there is this nice rule which says the intersection of these vanishing sets is just the vanishing set of the sum of the ideals, and the vanishing set of the union is the vanishing set of the intersection of these two. And so we can just take this as the definition on the level of affine subschemes. We say the intersection of these is the spectrum of R modulo the sum of the ideals. And note there's no radical appearing here, even though this would not change, taking the radical would not change the set, but it would change the affine subscheme. And so in this case, we just take the sum, and for the union, we just take the intersection. And then, so somehow we can, let's do this in an example to see that it actually matters. So let's take inside A2, so inside which we, some of the scheme associated to it is now the spectrum of kxy. We have two affine subschemes, one cut out by the ideal generated by y minus x squared. So this, the corresponding vanishing locus is in red here, and one cut out by the vanishing locus of y. So this x-axis here. And then if you take the intersection of these two things, by this formula, you should take the spectrum modulo the sum of two ideals. So it's just this ideal here. And then you see in this sum, so somehow this y allows you to get rid of this y here. And in fact, you can just use this y to eliminate the variable y completely. So this is actually isomorphic to the spectrum of kx modulo x squared. So this is this double point that we have already seen. So somehow this point now sits inside spectrum of kxy as a point, and it has kind of a bit of, somehow, at least in our pictures, we visualize it as having a bit of dimension along this x-axis. In particular, you see, if we took the radical here, then there would be a radical here, and then we would just get spec of kx modulo x, which would just be spec k, which would just be a single point sitting inside here. But instead, with this scheme theoretic intersection, we can kind of remember that this point has a bit of intersection multiplicity. In fact, so somehow we can reconstruct this by saying, well, take this intersection, so somehow this scheme here, and then look at the global sections, the global regular functions on this scheme. Then, of course, you can get back exactly this ring here. So this, these global functions are exactly this. And so if you take the dimension of this ring as a K algebra, if you remember it's a K algebra, and then take the dimension as a K vector space, then this has dimension 2 over K. And this 2 is exactly the intersection multiplicity of this red and blue curve at this point. In particular, kind of as a small application here, we can say if you have x1 and x2 inside A2K, any two curves not sharing any irreducible components, so here again in red and blue, then you have the associated affine subschemes, which is just this here modulo the ideal of these of the ith curve. And then if you take their scheme theoretic intersection, you get some affine subscheme of A2, or somehow of the spec K of xy. And now this affine subscheme, while it has an underlying topological space in particular, it decomposes into several connected components, like this. So here in this picture, these connected components would be this green part, which is basically where the two curves intersect. You have one connected component for each actual intersection point of these two curves. And then, in fact, this disjoint union, now this is really a disjoint union also as locally ringed spaces. So each of these Zi in themselves is a locally ringed space. And then you can exactly do what we did above. You can take the dimension of this ring of sections on Zi. And this turns out to exactly be the intersection multiplicity of these things at the corresponding point. So even if you were just interested in defining what it means to be the intersection multiplicity of two plane curves at a point, this whole scheme machinery would kind of give you the answer automatically. Of course, if you then actually want to calculate it, then it might be more useful to express this concretely in terms of the defining polynomials. But on a purely theoretical level, this is a way to define these intersection multiplicities. And this was not an unimportant problem. So for example, we have already mentioned them kind of in passing when we discussed this Bézout's theorem, which said that if you have two such curves without common components inside P2, then the number of the intersection points counted exactly with these intersection multiplicities here is exactly the product of the two degrees of the curves. And so I think this is kind of a nice validation why this theory of schemes can be important, even if you're just trying to talk about some classical questions. Okay, so this was everything about closed affine subschemes, and now in the next video we're going to look at open subschemes and distinguished opens and try to put some scheme structure on them.